An interesting problem to study in 2D kinematics is the problem of what angle will yield the largest range, range being defined as the distance from the initial starting point of a projectile to the ending point of the projectile. Now what we want to do first is remind ourselves about what happens to our kinematic equations when we are talking about projectile motion specifically. So up here in the top right corner you have the kinematic equations for reference, and you recall that one important consequence of projectile motion, essentially two-dimensional free fall, is that the acceleration in the x direction, ax, equals 0 meters per second squared. In other words, there's constant motion, or v initial x equals v final x in the x dimension. Now what this results in, if you look at all four of these x equations, the consequence is that the only equation we really have to work with is that your final position, or your range, in this case your maximum range, simply equals your initial position, if you choose it to be something other than 0, plus your v initial x times t. Now also in the y dimension, we know that in projectile motion, the acceleration in the y dimension will be simply g, or the acceleration due to gravity, negative 9.8 meters per second squared. Now because there is acceleration in the y direction, all four of our y kinematic equations will still be applicable in this situation. Now the problem that we're going to work with is probably a little bit familiar to you, but it's simply a kicker kicking a football from some starting point down on the ground. It will travel up, reach a maximum height at some time t, and then it will travel back to the ground at some other time t in the future. And a couple important points as we go through this problem is we're working with a problem where your initial y position equals your final y position. We also know that if that's the case, your initial y velocity, the initial y, will have to be equal and opposite to your final y velocity. If the ball starts and ends at the same height, it will be going up with the same speed that it comes down with. This is a totally symmetric situation. So now back to the question. The main question is, what angle yields the largest range? Well, let's look at the largest range. What determines the largest range is the time of flight. The time of flight of the projectile is what will determine how far that projectile gets to go. In other words, its range. And so the time of flight is going to be determined by the y dimension. So using the first kinematic equation for the y dimension, we can see that the time of flight will simply equal the final y velocity minus the initial y velocity divided by the acceleration, which we know over here, that'll be the acceleration due to gravity eventually. We'll leave it as a, in this case, a sub y. So that's the time of flight, and the time of flight will factor into the range equation, which we said over to the right was simply just v initial x times t. So that time in the y dimension is eventually going to make its way into our range equation. So far we've been able to populate a little bit of our inventory. Let's go ahead and finish that off. So for the x dimension inventory, the final x position, that's going to essentially be our range. And we don't know what that is. We just want to make that a maximum at this point. The t values, which show up in both the x and y inventories, we know that that is a shared value. And we're going to find that, or at least we can represent that as t equals vy minus v initial y over ay. Now, We also remember from the previous slide that the initial y velocity, moving down to our y dimension, the initial y velocity and the final y velocity are equal but opposite. So in other words, the final y velocity, we can just represent that as negative v initial y. Okay, and so that leaves essentially v initial x and v initial y as the two variables that we haven't been able to deal much with. So you'll recall that because the kicker is kicking this ball up and to the right with some initial speed v initial and initial angle theta, there are two components, one of which is the x component, the horizontal component of motion, v initial x, and we also have the vertical component of that, v initial y. And even though we don't know numbers for theta or v initial, we can represent v initial x as simply v initial times cosine of theta, and v initial y is v initial sine of theta. At this point, you should be able to see that fairly quickly and write those relationships down. So if we plug each of these in, so I'm going to plug my x velocity into my x equation, and I'm going to plug my y velocity into my y equation, we start to make a little bit of progress. So this will just be x equals, or my maximum range eventually is v initial cosine theta times t, and what we get over here in the y dimension is t equals, now stick with me here, vy final is just negative v initial y, right? So if I plug that in, I simply just get negative 2 v initial y, which is just 2 v initial sine of theta. And of course we're dividing by a sub y, which at this point I feel pretty confident in saying that is just g, the acceleration due to gravity. Now that we've set up our x and y relationships, we can see that my time value, which I gathered from the y dimension, and the time value in the range equation for the x dimension, are really the same time values. Remember, time doesn't depend on any particular dimension. So, in other words, because I'm looking for the maximum range, I want to work with the range equation. So I'm going to take the time value, which I didn't know, and I'm going to plug my y time value in for my x time value, because they are the same time values. And what that results in is, if I make that substitution carefully, and I'm going to do this on the fly here, is I get a v initial from the x dimension, but I also get one from the y dimension, so I end up with v initial squared. I also end up with a negative in there, so I want to preserve that negative for now. We'll deal with that in a second. I get a sine theta from the y dimension, but I also have a cosine theta for the x dimension, and that's all over the acceleration due to gravity, g. Now you may look at this and say, well, I'm not sure how to optimize for theta because sine and cosine are kind of different values, and so you would be right. Oh, I forgot. I actually have a 2 in there, so let's not forget the 2. But if you recall from trigonometry, 2 sine theta cosine theta is actually, via trig identity, simply just sine of 2 theta. It's a double angle trig identity. So we can go ahead and revise our range equation to reflect that. So a negative v initial squared times sine of 2 theta divided by g. Now let's go ahead and deal with g for a second. G is simply negative 9.8. So you can see this, and if we take g and replace it with negative 9.8, we're going to get a negative value on the bottom, negative value on the top, and those will both cancel each other out. And so I'm just going to change those both to positives. Now, what I have to remember is when I go ahead and plug in for g that I'm going to plug in the positive value. Otherwise, you can leave g alone. and just remember to plug in the negative value for it. Back to that sine of 2 theta, that's really important because if you look at what we have now with this range equation, we have an equation that is a function of theta. It's also a function of initial speed and the acceleration due to gravity, but in a given problem, those two values, the initial speed and the acceleration due to gravity, don't really matter because remember our question was what angle yields the largest range. That's for any v initial and for any acceleration due to gravity. So we're really just concerned about maximizing my sine of 2 theta. So how do we maximize the sine of 2 theta? Well, you may recall from trigonometry, you have your unit circle of radius 1, and the sine value is a maximum when the angle, or its argument, is 90 degrees, right? The sine value, or the y value, is 1, the largest value that sine can take on when your angle is a right angle, a 90-degree angle. So what does that mean? Well, that means we simply want the 2 theta to equal 90 to maximize our range, or our value for that sine value. So what does that mean? Well, 2 theta must equal 90, so theta equals 45 degrees. If I make theta 45 degrees, what happens to my range equation? Well, sine of 2 times 45 is 90, so the sine of 90 degrees will be 1, and my range is v initial squared over g. If I make theta anything else at all, it will lower the value of my sine 2 theta, and thereby making the range slightly smaller. So that's why the angle which yields the largest range, which was our original question, is 45 degrees. Now keep in mind, this is only true when you start and you end at the same height. And the reason for that is because we made a pretty important assumption over here that your initial and your final y velocities are equal and opposite each other. So you want to be careful. I know the book gives this equation to you and says it's a special equation called the range equation. It's really not. It's a derived equation, which you can derive like I have done from first principles. And you really don't want to start with this equation because if you use it wrong, or you're wrong about what the equation actually entails and you forget the squared value, or if anything happens like that, you're not going to be able to get credit for setting it up from first principles.